Hello guys, welcome to the machine design world. This is Keval Patil and today we are going to see design of spring under varying loads. In last video we already covered design of spring using static approach. So let's go for the video. Okay, let's start with the problem. Design of spring under varying load PSG 7.102. Okay, so I have already opened PSG page number over here. You can read spring under varying loads. I have little bad throat today, so pardon me. Okay. Problem reads: design a helical wall spring for an operating load range of 600 Newton to 1200 Newton. First thing, it is helical compression spring and maximum load is given 600 Newton, 1200 Newton, and minimum load is given 600 Newton. That's why it is varying load. So load is varies from 600 Newton to 1200 Newton. The compression at the maximum load is 25 millimeters. So after application of 1200 load, what will be the deflection of the spring? 25 mm. The spring index is 6. C is given as 6. The permissible endurance shear stress for the spring material as 480 megapascal. Okay, so endurance shear strength given 480 megapascal. Then yield strength in shear as 960 megapascal and modulus of rigidity as 80 kilonewton per mm square. So what value is given? P max 1200 Newton, P min 600 Newton, Y 25 millimeter, C is equal to 6. So here I used same notation which are used in PSG. Okay, so tau 0 for endurance shear strength and tau y for yield strength in shear. Alright, modulus of rigidity G 80 kilonewton per mm square is equal to 80 into 10 raised to 3 Newton per mm square. So let's move to the answers. Okay, now first see here in this PSG it is given actually all formulas to solve this problem, almost all formulas. Okay, so first thing, this is tau A. Okay, so it is nothing but amplitude shear stress and tau m is mean shear stress. Okay, values are given, the formulas are given, but for that we need PA and you have PM. So PA is nothing but amplitude load and PM is nothing but mean load. So first we will find these two, PA and PM. We'll put over here, we'll find tau A and we'll find tau A and tau M, and then we'll put over here to find the wire diameter. So first step is to find wire diameter. Okay, so first we will find amplitude load. Okay, amplitude load also called as PA. Okay, formula is PA is equal to P max minus P min upon 2. Actually this amplitude load and mean load formulas you will see in fourth module, that is fluctuating loads or design against fluctuating load. Okay, so P max is 1200 minus 600 divided by 2, it is nothing but 600 by 2, so 300 Newton. Similarly mean load PM, so PM is given as P max, mean is nothing but max plus mean upon 2, so it is 1200 plus 600 divided by 2, so 800 by 2 is 900 Newton. Now we having this max load, mean load. Okay, so let's find wall stress factor. All right, so wall stress factor, okay, denoted as Ks. Okay, why we finding? Because we want to find this tau A time and whatever value given in this formula we want to find that value. PA we having, we need to find Ks, KSH, and both the Ks and KSH, that is wall stress factor and shear stress factor, direct shear stress factor. Okay, so wall stress factor Ks is given as 4c minus 1 upon 4c minus 4 plus 0.615 divided by c. You know the PSG page number you have seen in the last video, then you must be knowing it is PSG 7.100. Right, so let's find it. C is given as 6, so 4 into 6 minus 1 upon 4 into 6 minus 4 plus 0.615 upon C is 6. So if after calculation you will get value as 1.2525. Alright, now we know that whenever we are having varied load or fluctuating load or fatigue load, that time we have to use wall stress factor. For static load condition we use direct shear stress factor KSH, but here we need that value in this formula, so we have to find KSH also, but we can't use the formula. We know the formula of KSH 1 plus 0.5 upon C, but that was derived using static approach. So how can we derive the formula over here? Okay, so for wall stress factor, here wall stress factor, in front of this you can see the formula given. Wall stress factor is nothing but KSH, that is direct shear factor, into KO, that is curvature factor. Okay, so now KO is equal to curvature factor. I'm just writing, you don't have to write this in exam. Curvature factor, okay, don't write anything like this, direct write KO is equal to, see value is given here, KO is equal to, for C3, 4, 6, 3 different values, for 6 it is 1.15, so it is 1.15, PSG 7.102, PSG 7.102. Alright, so now you are having value KO, you know the relation, so KS is given as KSH into KO, it is given over here only. So you can find KSH as KS, that is 1.2525 divided by KO 1.15, and you will get the answer like 1.0891. So now you having KSH and all, so you can go for this formula. So amplitude shear stress, amplitude shear stress tau A is first formula. So we are not having diameter, so we can use this formula. Okay, so it is given as 8 tau A is equal to 8 KS into PA into C divided by pi d square. Right, now I'm just putting the values. 8 into 1.2525 into PA is 300 into 6 divided by pi into d square. D square value we don't know, I'm just keeping that as it is, and after calculation you will get 5741.03 upon d square Newton per mm square. Alright, similarly you can find mean stress value, okay, here mention PSG page number, PSG 7.102, here also it is PSG 7.102. so taking formula from PSG. Okay, so mean stress value tau m is equal to, again same formulas, only difference is here it is KSH and here it is P mean into C upon pi d square. So it is 8 into 1.0891, PM value was something 900 into 6 upon pi d square. So after calculation you will get 14976.2 divided by d square. Alright, so it is also in Newton per mm square. So this is tau A and this is tau. So we having tau m and tau m, so we can go for the next formula, that is factor of safety formula. Okay, factor of here it is denoted as n, and we know the value of factor of safety for spring, it varies from 1.5 to 2. So just considering or assuming n is equal to 1.5. I'm just assuming it 1.5. You can assume 1.6, 1.7, depends upon you. Okay, but I'm assuming 1.5. Usually in most of the books they assume 1.5. Alright, so the formula reads 1 upon n is equal to tau m minus tau a divided by tau y plus 2 tau a divided by tau 0. This is from PSG 7.102. Alright, now I'm just putting the values. 1 upon 1.5 is equal to, now tau m is 14976.2 upon d square minus tau a is 5741.03 upon d square divided by tau y. Tau y value, we know the tau y value, or tau y value is 960. So it is 960 plus 2 into, what is tau a now? Tau a is this 4710.3 upon d square. Tau 0 value, we have seen the tau 0 value, it is nothing but 480. So 480. Okay, now put this equation in calculator and find the answer. Okay, remember don't push this 0.2 and 0.03 value, or otherwise your calci will say like I am out of my limit. Okay, and it won't fit in the formula. So just remove this, because these are big value and this 0.3 doesn't matter that much. Okay, from this you will find the diameter, you will get 7.09 mm. Alright, 7.09 mm. Now we can go for the PSG 7.105. There we can find the standard diameter. So you can see 7.10, so it is between this. So next standard diameter is 7.5. So selecting 7.5. So selecting D is equal to 7.0, so 7.50. Okay, 0 from PSG 7.105. Alright, so now we found diameter of wire D 7.5 mm. 7.5 mm. So next, all the things like mean coil dia, number of coil, it is same as a static approach. Okay, we'll solve one full problem, so we'll go for that now. So next term is mean coil dia. So we know the formula, C is equal to D by D. So from this, D is equal to C6 into 7.5. So you will get 45 mm. Right, then we know the number of coil formula. Okay, find number of coil. This is same as static approach. Okay, coils n. Now we are not having spring stiffness, but we are having maximum deflection Y. We know the formula of Y. Y is equal to 8pc cube upon n upon g into t. It is given in PSG 7.100. So this is the formula. PSG 7.100. So what all we know now? So y is 25 mm given is equal to 8. Load, here you have to consider maximum load because this deflection is for 1200. It is mentioned that the compression at the maximum load is 25 mm. So we are considering maximum load. C is equal to 6. Number of turns we have to find. G is given as 80 into 10 raised to 3 Newton per mm square. Diameter is 7.5. So from this equation we will find n as 7.23. So we will take 8 turns. Okay, it is turns, so it will be full or whole number. Okay, now we'll go for total coils. Okay, so which coil we select? We select square and ground 8. You know why we select this ground? I have explained in the last video. Okay, it having advantages over those three. So selecting squared and ground end. Okay, PSG 7.101. Okay, so we know the total number of total coils, given formula in PSG 7.101 itself, n dash is equal to n plus 2, so it is 10. Alright, so after having this n plus 10, see the formula, we know this formula, n plus 10. Now we can go for the solid length, and the formula is given on same page number, that is dn plus 2d. Okay, for solid length which is dn plus 2d. So solid length ls, so ls is equal to dn plus 2d. d is 7.5, n is equal to 8 plus 2 into 7.5, so you will get solid length as 75 mm. Just calculate and see. Alright, now we know free length LF. Okay, what is formula for LF? Is equal to LS plus y plus 0.15 y. So LS is 75, y is 25 plus 0.15 into 25. You will get 103.75 mm. Alright, so now we will go for pitch. Okay, just mention PSG page number over here, PSG 7.101. Okay, so pitch formula, we know the LF value, LF formula, it is given on PSG, that is Pn plus 2D. Again it is PSG 7.101. Okay, so LF is 103.75 plus pitch, number of turns are 8 plus 2 into diameter is 7.5. So here, from here you will get pitch as 11.09 mm. So you now you know the pitch, you can find helix angle. So formula for helix angle is phi is equal to tan inverse p upon pi t. Okay, so it is tan inverse p value is 11.09, which just now we got, upon this pi value is d value is 45, I think 45, so it will be 4.48 degree. Okay, so this was same as static approach. Okay, after finding d, it is same for the static same as static approach, but sometimes they add one more thing, find energy store in the spring. Okay, so we'll find energy store in the spring, find energy store. Okay, this is the question, find energy stored in the spring. Okay, this is the question. So energy stored is nothing but resilience. They ask resilience, that is U. Okay, and the formula is given in PSG 7.101. 7.100, it is given as P into Y into Y by 2. So this P is nothing but maximum force, Y is a deflection, and divided by 2. Okay, so U is nothing but resilience or energy store. Okay, so that is nothing but U is nothing but P 1 by 2 into P into Y. Here P you have to consider maximum load, so it is 1200 into 25, and you will get something 15,000 Newton mm. So Newton mm, we know the energy in joules, so we have to convert it into Newton meter, that is nothing but joules, so it is nothing but 15 Newton meter, or you can say 15 joules. So 15,000 Newton mm, it is nothing but 15,000 Newton meter is nothing but joules, so energy in joules. One more thing they add, that is find solid stress. Okay, in last video I forgot to explain that, so in this video I will explain the same. Okay, so solid strength or solid stress, or they say check for solid stress. First thing is, for this let's understand what is solid stress. Okay, it is a stress induced in the spring at solid length. Okay, just understand, this is a free length. Okay, we applied maximum load of 1200 Newton. Okay, that time deflection was, it is different one, so that's point time deflect was 25 mm. Okay, so it deflected by 25 mm and it came over here. We are applying maximum load, and or we are applying P max. Okay, there he is, the spring is moving like this. Okay, is deflected by this, but it is not a solid stress. Okay, solid length is what, when the coil touches to each other. Okay, so this we consider as y as something. Okay, 65 mm, in our problem it is 25 mm. Okay, now this 0.5, while calculating LF is nothing but this LS, this one is LS, solid length, LS plus 0.5 y plus y. Okay, so after we apply maximum load P max or P solid, we will get LS. After applying the 1200 Newton, we got this length. Okay, and after applying maximum load or solid load, we will get LS. Okay, so this is after applying, if you are having range about 200 to 400. Okay, after applying 400 we are getting this value, and for solid length what we will take, it is P max or P solid. Okay, so first we have to find maximum deflection. It is nothing but y plus 0.5 y, or you can take LF minus LS, it will be the maximum deflection. Okay, so max deflection, y max. Okay, so y max is LF minus L solid. So LF we know something 103.75. solid length we know it is 75, so 103.75 minus 75, and you will get 28.75 mm. Alright, so next is shear stress at solid load. Shear stress at solid length. Okay, so tau s, we know the value from PSG 7.101, the PSG 7.101, so tau s value. Okay, now we having tau, so we know for solid length we will use tau s. Okay, so this formula we will use. Okay, so it is nothing but KSH into 8. Now which load? Maximum load or P solid, which is acting on the spring at solid length. Okay, into D divided by pi d square. So we have to find this P solid, and this P solid is given as y max G into D divided by 8c cube upon ac cube. It is, so we know the y formula, it is 8pc cube upon n into GD. So if we are having solid strength, we are having already y max. Okay, so we can use same formula, y is equal to this. Here we using y max, so P solid we have to use. Okay, here we using y max, P solid, so P solid will be y max into GD, so y max into GD divided by 8c cube upon n. So just put the values. Y max is given as something 28.75 into value of G is 80 into 10 raised to 3, value of T is 7.5 upon 8 into C cube is 6 cube, number of turn size again, and you will get P solid as 1247.82 Newton. Now put this value over here and find tau max value or tau s value. This is P solid, and tau s value you will get putting this value over here. KSH is 1.25 into 25, 1.2525, 8. P solid is this value, D is again 70.5 pi. So this is C. This is C value. Okay, so C into pi into D square. C is 6 and D is 7.5, and you will get value at 4 to 4.5 Newton per mm square. Now we have to check the solid stress. Okay, let's check for solid stress. So it is given in PSG 7.101. Check for solid stress. We are having two values, TS or tau s 0.5i for hard drawn carbon steel and 0.6 for alloy steel. Okay, so I'm using this formula, more chances to get self. Okay, for alloy steel, so it is 0.6 into sigma u. So assuming spring is made up of alloy steel, so what is the formula? Tau s should be less than 0.6 sigma u. So it is PSG 7.101. Alright, so for this problem sigma yield is not given. Okay, in case, so they want to ask about solid stress. If it is asked, like in last problem they have asked, and their sigma u was given as 1196 upon d raised to 0.168. So in case if it is given, then permissible stress will be this whole 0.6 into 1196 divided by 9 d raised to 0.168. Just find the value. Okay, you will get something this value, and check whatever we calculated, the tau is we just now calculated, that is 4 to 4.5. so this value should be more than tau s, then spring in is safe in solid stress. Okay, so I think for varying load, I will in next video we'll see 2 or 3 variation. It is not that much big variation. You can see first few steps are different, not that much different again. Then too we will see 2 problem at least. Okay, thank you for watching the video. Let me know whether you understood or not. Okay, just comment. Thank you.